All right, so today we're going to go ahead and look at 3.6 derivatives of logarithmic functions. So we've talked about all of these different trigonometric, uh, inverse trigonometric, implicit, power rule, product rule, quotient rule, all of this stuff and how we take the derivative or how do we deal with those. So today we're going to move on to, I believe this will actually be our last derivative rule that we'll be covering for the semester, I believe, maybe. We're going to talk about the last group are logarithmic functions. So let's just go ahead and just do a quick recap of something that we do already know. The exponential function. So can someone go ahead and give me the derivative of e to the x, for example? Yeah, derivative of e to the x is e to the x. And it looks like this thing's going to be flipped, so I'm just going to flip it in afterwards. So we know that the derivative of e to the x is, in fact, e to the x, like so. This is something that we learned probably in our first time about learning about derivatives. All right, so we know this. So let's just do some practice with what we know about e to the x. Example 1, let's go ahead and get the derivative dy dx given that y is equal to e to 3x squared plus x. So we're just doing some recap about exponentials before we talk about logarithmic functions. All right, so looking at this example 1, what rules am I going to need besides derivative of e to the x? So I'm hearing a couple of different rules. So let's just go down the list. I definitely need e to the x. Do I need a product rule here? I would say here I don't need a product rule because I'm not multiplying anything, right? I have e to a power. So I'm not multiplying anything necessarily. I don't need quotient rule. I think we can agree that there's not a quotient here for us to look at. Do I need chain rule? Yeah, I would say that we need chain rule. And it looks like I'm not going to need trig or inverse trig derivatives either. So let's go ahead and list our layers of the function. We know if I want to talk about chain rule, usually we've gotten to the habit of listing out the layers of the function. What is layer number 1? Yeah, e to a power, right? E to a x variable power, if I want to be exact. E to some power. What's my second layer? Yeah, it's going to be this whole power. The reason I know that there's not going to be any more layers is that we know how to take the derivative of this directly, 3x squared plus x. That's usually a big hint saying, okay, I don't really have any more layers after that. Whenever I can look at it and say, I can get the derivative immediately without breaking it down further. All right, so if I go ahead and look at the derivatives of these layers, derivative. What's the derivative of e to a variable power? It would be the same thing, e to that same power. And I started using this little notation to say whatever was in this blank still goes in the same blank that I had here. All right, and then we need a derivative of the inner layer. What's the derivative of 3x squared plus x? Yeah, we got 6x, come on, 6x plus 1. All right, so I've identified the layers and the derivatives. And now I can just go ahead and take the derivative, dy dx. I have first layer. I write e to whatever power, or in this case, 3x squared plus x times the second layer derivative. So I'm just going to write times 6x plus 1. I put out all my layers, so I know that I am in fact complete. So my final derivative being e to the 3x squared plus x times 6x plus 1. So this should be a little bit of a review for us about chain rule and e to the x. Any questions about how we did this example 1? I'll give y'all some time to copy it down as needed. So again, let's go ahead and do another practice example with e to the x, just so that we know that how to handle these for sure. So I'm going to go ahead to example 2 for now. Example 2, and y'all kind of saw this already before. We have, it's a little bit cut off, but we have e to the e to the e to the x to the second power. Minus x, just to put something a little extra at the end. So looking at this function, let me go ahead and write this 2 so that's very clear that this is supposed to be x squared here. I think we can all agree that that minus x is not going to really give us a problem on taking the derivative. We know how to get the derivative of negative x. So I know that if I want the derivative of this, dy dx, it's going to be something, the derivative of whatever that is, minus 1. Because the derivative of negative x is negative 1. So really, let's just focus on getting the derivative of this expression right here that I have. That's what we're focused on. So again, we have the exponential function, and I have a lot of layers to this function. So once again, as per usual, let's just list out the layers and then the derivative of that layer. Derivative. All right, so layer number 1. What do you think layer number 1 is? Yeah, so if I look at this, what I underlined, I would say that my first layer is e to a power, for example. So that kills off this layer. What's my next 2 layers? If I look at the next layer and the layer after that, it's still e to a power, right? So I might just do that for layers 2. That's accounting for this one. And layer 3, e to that. What's my 4th layer? Yeah, I got x squared. We can put x squared because we know how to take the derivative of x squared instantly. I don't need to make a 5th layer for that. The x. Oh, so I've already accounted for this one. We already know what the derivative of minus x is, minus 1. So this table I'm doing is mainly for this complicated part. One, 2, 3, 4. I listed 4 layers, so I need to get 4 derivatives. The good news is we know what the derivative of e to a power is. It's going to be e to the same power. E to a power, e to a power, e to a power. And just to very clearly make sure what we know is in each e, this was the outer layer. These are going to be the same whatevers. Whatever was in my second layer, I'm keeping that the same. And whatever's in this third layer, I'm keeping that the same. What's the derivative of my 4th layer, by the way? Let's go ahead and do that. Yeah, so we have 2 times an x, so 2x, just from our power rule. All right, so I've got everything I need for the derivative. I'm going to erase this one because I'm going to figure that we're going to need a little bit more space here. Layer number 1, this is e to the, we gotta be careful about what's in this layer. This came from my first layer. My first layer was e to all of this. So I'm just gonna rewrite that. E to the, come on, e to the e to the e to the x squared. That finishes layer number 1. Again, if I want, I can look at this and say, I've cleared off this layer. Layer number 2, I had e to the x squared. So I'm going to keep it as e to the x squared, because that second layer was e to the x squared. Third layer, I have e to the, what's the power for my third e? Yeah, x squared. Again, my third layer was e to the x squared. So if I'm doing a matching, I'm going to just keep it the same. And then we multiply by the last one. This board does not want to cooperate very well. Times 2x. And we still have that minus 1 for the other part. So I have my final answer. Dy dx is equal to e to the e to the e to the x squared times e to the x squared times e to the x squared times 2x minus 1. Breaking down all of the layers of my function as needed. All right, so we've already done exponential functions. So why would I bother talking about exponential functions whenever the title of the section is supposed to be talking about logarithmic functions? Not that they can operate the same, but one thing that the next slide is going to show you, we know that e to the x and logarithms actually have a special relationship between each other. Before I do that, any questions about this example 2, just going through any parts, anything like that? All right, so let's go ahead and talk about the relationship between e to the x, and in particular, the natural log of x. This is actually a little bit of more or less algebra concept that we're bringing back. So one of the things that we did in algebra was a lot of trying to do the opposite operation. So like if we had plus 2, the opposite would be minus 2. The opposite of times 3 would be divided by 3. We even did this with more complicated stuff like the square root. The opposite of a square root is squaring. And we called those inverse functions. So using that idea, as it turns out, e to the x and the natural log of x are inverses of each other. And if I want to be a little bit technical, that means whenever we do our function composition, we can say that they quote unquote cancel each other out. That is, if I do natural log of e to the x, I get x. Or if I do e to the natural log of x as a power, that cancels out and gives me an x. That's the first property. Furthermore, the second property tells me I can write y is equal to natural log of x if and only if x is equal to e to the y power. And then the last one being, whenever I look at any random number b to the x power, assuming b is positive, then I can do e to the natural log of b to the x, which is equal to e times x natural log of b. So these are actually using properties of logarithms about playing around and moving stuff left and right as needed. Yeah, so we got natural log of x and e to the x, right? Two different functions. The long story short is that these, if we want to think, they can cancel each other out. So if I ever give you something like this, for example, I'm going to use an actual number. If I gave you natural log of e squared, natural log and my e are actually going to be opposite operations. They cancel. I'm going to get 2, or whatever that power is. And then we have the same thing over here. Let's say I add e to the natural log of, I don't know, 7. Then this is just going to be a plain 7. So these are opposite operations, kind of like how we have x squared and then the square root of x. If I do the square root, that's an ugly square root. If I do the square root of x squared, that's a plain x. Or if I do it the other way around, the square root of x squared, I still get x. So this is sort of in the same vein. Whenever I combine them together, they actually cancel each other out, leaving me with, well, whatever was left over. In this case, 2 or 7. So these are some properties, but I'm not actually going to be asking y'all like to give me these properties. These are more like the background about how I get the derivative and stuff like that. And I'll take a moment to talk about this second one. Why is it true? The second property is actually a direct result of the first one. Let me erase this bottom group here so that I have space to write it out. So on the left, I have y is equal to natural log of x. Well, one of the big rules about algebra is as long as I do it to the left and the right side, then typically we say, all right, that's legal. We can keep it equal to each other. So if I look at this equation and I take e to the y power is equal to e to the natural log of x. This is still allowed because I did it to the left and the right. Well, e to the y, there's not much we can do there. We have e to the y. E to the y. But then e to the natural log of x, from the first property, we know that these will actually cancel each other out and leave me with an x, which is what we had over here. So this is just more or less of a recap of algebraic properties of logarithms and exponential functions, particularly logarithms. So here's the reason why. I'm going to go ahead and derive the derivative of the natural log of x. Let's go ahead and clear this. Let's say I want the derivative of this right here. Right now, we have no idea what the derivative of a natural log is. But I know that this equation means the same thing as what I have over here. Well, if I write it like this, I know how to take the derivative of e to a power. So let's focus on this side. What's the derivative of x? We get 1. What's the derivative of e to the y power? Yeah, we have e to the y. And because it's not a plain e to the x, we're doing a derivative of y. We had to put that dy dx deal next to it. So times dy dx. Okay, so let's see if I get my derivative alone. What I can do is divide by e to the y on the left and the right, giving me dy dx is 1 over e to the y. So that looks a little bit weird, but we're going to take it one step further. Let's say I want my derivative to only have x's. The question would be, how could I get rid of that y if I'm looking at number 2? Yeah, so if I look at this, I know what y is. Y is a natural log of x. So this is the same thing as 1 over e to the ln of x. But what do I know about e to the ln of x? It cancels out because we have right here e to the ln of x. That's a plain x. So if I take all of this together, sorry I'm a little bit everywhere, dy dx is 1 over x. So if I have y is ln of x, we know the derivative is 1 over x. This is a little bit of a roundabout way of getting the derivative, technically through our implicit differentiation. So this is me more or less proving what the derivative is. And that's actually what we're going to see on this next slide for our theorem. Yeah. Yeah. So the reason is that if it was e to the x, you would say derivative is e to the x, right? But because it's not a plain x, we are technically doing the chain rule. So let me clear this. If I look at e to the y, first layer is e to a power, second layer is y. Derivative of e to a power, we get e to a power. Derivative of y is dy dx. So that's why I had e to the y times dy dx. Long story short, if I ever say derivative of y, we have to write that at the end. All right, so, but that's not going to be our main focus for today. That was just deriving where the heck did this other theorem come from. So let's go ahead and talk about this theorem right here. We have the derivative of the natural log of x is 1 over x if x is positive. If I look at that first line, why can I not plug in a negative number for the first line? Why does x have to be positive? Well, if I go into your calculator and I type in natural log of, I don't know, -8, it's going to give you an error. We can't do natural logs of negative numbers. So the second one is just an extension of it saying, what if I do want to deal with negative numbers? Fortunately, all we had to do is say the natural log of the absolute value of x is still 1 over x. So this is just me being a little bit careful, covering all my tracks and saying, if I want to be very formal, we have to include, is x negative or is it positive? But really, in the long run, we're just saying derivative of ln of x is 1 over x, one way or another. And as I said, this will be our final derivative rule that we actually learn for the semester. This is the natural log function. And technically, you could deal with a regular log function like log base 10, probably like what you used in chemistry. We might have time to talk about that later. But for right now, we're going to talk about the natural log. The reason why is that if we want to be technical, I can really convert any logarithm into natural logs if I want to. All right, so I'll give y'all some time as per usual to copy this before I go on to example 3. Oops, what happened? Let me go ahead and pull that again because it crashed. Let's see if it opens. There we are. Bless you. So we had this theorem here. Oh, so this one is, it's called natural log, ln. So whenever you see me, yeah, that's why whenever I'm writing it, you're often going to see me write it like this with ln, just so that we don't mistake it for like a 1 or an I. All right, so it looks like this board does not want to cooperate and continue any further because it is not showing up any of the drawing tools, which means that it is very close to completely crashing. So that means I will have to cut it here today before the thing just decides to crash completely. All right, so besides that, I will see y'all on Monday. We're going to go ahead and finish this on Monday. We only had, well, we actually had a fair bit of stuff to look at, just different examples and everything like that. All right, I'll see y'all on Monday. Let me go ahead and end this here.